Alright, so today we're going to discuss multiple bonding. Multiple bonding and when you have a unique atom conflict. So we're on page 6 of the bonding guide. So multiple bondings. It says, what happens when the number of electrons from step 4 is not the same as the number from step 1? Basically, you're building your thing. You find out at the end you don't have enough electrons. Well, keep in mind that most of the time atoms are bonded to another atom by sharing a single pair of electrons, which is known as a single bond. That is a sigma bond. That is kind of like a handshake. Like you get these electrons in here kind of making, that's like kind of like a handshake. It's just a sigma bond. If that doesn't work out, if there's not enough electrons in there, then you will find that, nature will find a way. If these things are to be made, they will find a way. So let's do oxygen, for example. So we have oxygen, OO. Now if we take a look, each of these have 6 electrons each for a total of 12. We find we have 2, 4, 6, 8, 10, 12, 14. We are showing 14. That's no good. We need to only be showing 12. So the way you do this is you pick, you basically need to make another bond. This is called a double bond. Oh, unfortunately I don't have any whiteout. So let's start this again. So we have 2, 4, 6, 8, 10, 12, 14. We can only have 12. So what we need to do is basically make a double bond. When we do that, we need to get rid of 2 others. Normally I would white those out. Obviously I'm going to have to redraw it this time. But we get that double bond, and then we have 2 others, 2, 4, 6, 8, 10, 12. So basically we put a bond in, and then we remove 1 pair from each. Because remember, what we're trying to do here is get that down to 12. So if we put another bond in, then it's going to be 2, 4, 6, 8, 10, 12, 14, 16, which that puts us now 4 over our original 12. If we put the bond in, basically we are, when we remove 1 set, that makes up the one from the bond. And when we remove the other set, that brings our number down to what it should be. Quite easy on that. Try these on your own. Maybe pause the video. 3, 2, 1. Alright, so if you didn't pause it, then this is a spoiler for you. We have nitrogen in. We have 5 plus 5, which is a total of 10 electrons. To make this normal, we would do 2, 4, 6, 8, 10, 12, 14. But that puts us 4 over. So if we put a double bond here and we take out these 2, we are still at 2, 4, 6, 8, 10, 12. We only have 10, so that means we need another one. Then we would take out these guys, 2, 4, 6, 8, 10. I'm going to rewrite it again, 1, 2, 3. That is a triple bond. So we have a double bond with the oxygen and a triple bond with the nitrogens. Now, if we were to look, you might ask a question like, why did I put these out here? Well, keep in mind that all electrons are negative. So if we did not put those out there, then basically they would be repelled to out there. So if we left them here, they would be repelled. You want to put them as far away as you can. Again, keeping in mind I have that symmetry. Same thing with this. This is okay, but it does show a little bit more understanding if I put them like that, because they're going to repel each other as much as they can, right? We get like a little ET. Phone home, phone home, phone home. Keep in mind that that only has 2 bonds, though, a double bond. So we said that a single bond is a sigma bond. That's a single bond. A double bond has a sigma bond. And it also has what's called a pi bond. So if we imagine the sigma like a shake of the hands, the pi bond is in reality kind of like this out here, kind of a reach around kind of thing. Basically, that's like if you're shaking hands and you pat somebody on the shoulder at the same time. Now, a triple bond has a sigma bond, which is that handshake, and then it has 2 pi bonds, 2 times the pi bond. So it's like handshake, pat on the shoulder, and then you're doing like a Gracie Jiu-Jitsu, like leg grab or whatnot, you know, like some type of craziness. But basically what that means is you have the handshake, and then you have, imagine we have this kind of bond that's kind of the pat on the shoulder coming around, you know, this would be right in front, this might be on the top, and then you have another one kind of doing the same thing around the side. And basically all these electrons are trying to, you know, keep their distance from each other while still maintaining each of these to have that octet rule. Draw the Lewis structure of carbon dioxide. So, carbon dioxide in the center. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 4 plus 12, which equals 16. So we are 4 over. So there's some options here. We could get a triple bond on one side, do a triple bond here, and then take 1 and 1 away. The problem with that is that does not match our symmetry. So what is more likely to happen is we get a double bond on each of the sides, 2, 4, 6, 8, 10, 12, 14, 16, and we don't have that uneven symmetry. So this is the better option of the two, and it is the most respected option. So then let's take a look at unique atom conflict. So what happens if you have, for example, H2CO or N2F4? Well, with H2CO, you don't really have a unique atom here. So you got to go with what I call the honk rule. HONC. Honk. This, hydrogens and halogens form one bond most of the time. So hydrogens and fluorine is a halogen, that's one bond. Never going in the middle if you can only form one bond. Oxygen forms 2 bonds, so it's possible. Nitrogen forms 3 bonds, probably in the middle. Good chance of nitrogen there, it's going in the middle. Carbon forms 4 bonds. Definitely awesome center of the molecule contender. So basically, as you look at these, okay, which one can form the most bonds? Well, carbon. Out of these, which one can form the most bonds? Nitrogen. But we have 2 of them. Let's save that for a second, for in a few seconds. So when we do this, there is another way besides honk. If you're looking at them and you see their electronegativity is lower, it's likely to go in the middle. The problem with this way is that if you even consider hydrogen for a middle of a molecule atom, you're going to be disappointed because it can only form one bond, even though it has a 2.1 for electronegativity. No way, no shape, no how. But between oxygen and sulfur, you're probably thinking sulfur's going in the middle. That would be a good point. Phosphorus and oxygen, phosphorus going in the middle. Remember, we're just in the basics now, so honk will get us through what we need right now, but just pointing it out for later. So if we count the valence electrons for H2CO, we get 12 valence electrons. So we're going to put carbon in the middle, and I'm ahead of myself, but too late for that. I'll just put it up here. Carbon in the middle. We get that. 2, 4, 6, 8, 10, 12, 14. Too many. So the only thing we can do if we have 14 and we only need 12 is we need to make a double bond. Carbon cannot make a double bond with the hydrogens. It's going to have to make it with this oxygen. When it makes it with that oxygen, remember, we take away 1 from the carbon, 1 pair from the carbon, 1 pair from the oxygen, and then we line them up. Keeping in mind that we're going to spread those out as best we can. Here's a step-by-step process of that. You're more than welcome to go through that. Let's try NOF here. N, O, or F. Well, we said that nitrogen has an electronegativity of 3 versus the O is 3.5 and the S 4.0. Or you could go by honk, meaning that nitrogen has 3 bonds that it likes to form. So nitrogen, oxygen, fluorine, that's 5 plus 6 plus 7, 11, that's a total of 18. 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is what we get. We have 20. We're over. Well, we do know that nitrogen and oxygen like multiple bonds. Nitrogen likes 3. It only has 2 currently. Oxygen likes 2. It only has 1 currently. So again, we're going to put that guy there. We're going to take away 1 from each. We get fluorine, nitrogen, oxygen. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's our 18. Here we have N2F4. The problem with this is we don't really have a central atom. And that's okay as long as we remember symmetry. So there's our N's. We have 4 F's to put around here. So they're not all going to be coming off of one N, but we're going to have some symmetry here. So we get 2 times 5 plus 4 times 7 is 38. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 27, 28, 30, 32, 34, 36. And I think I might need to recount these. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. Double count, yep. And that's what we get. We have the octet fulfilled for each one of these. Notice that even though nitrogen, well, it does have 3 bonds. Each of these nitrogens is fulfilled. We don't need a double bond or anything because we have the 38 electrons needed to make this. Very nice. C2H2. C2H2. Symmetry, right? So instead of having the H's come off of all one of them, we make that symmetrical. We have 8 plus 2, which is 10. We have 2, 4, 6, 8, 10, 12, 14. Right there, we're 4 over. We know we're going to need a double bond, either 2 double bonds or a triple bond. Well, we're not doing anything with these hydrogens because the hydrogens only get 1 bond. So it looks like we are making a triple bond. That's going to, each one of those is going to take away 2 sets of electrons, 1 from each carbon. So we get, boom, C2H2. Now you are asked to do 13, problems number 2, and 14, problems number 4.